Hi, this is Jimmy, ready to talk about the optimization project final report. First, let's focus on the background information. My project is about hexpod robots. The picture is an example of the hexpod robot. The hexpod robot of mine was designed to work on bad outside conditions in bad weather on bad terrain. In reality, it can work on a disaster area like an area after earthquake to import cargo there. As for related work, I was a part of a team doing research on hexpod robots, and my research focused on robot stability related to topography and friction. There is a paper to indicate that, which is shown in reference below the slide. I also did research on how possible for the robot to lose control and how to avoid death by switching patterns of gates. And for the robot model, the picture shows the robot model in Adams, and the table shows some parameters of the robot, the mass, the length, and so on. Then I will talk about some gates that I will use in the optimization program briefly. How they work and the legs face due to the different duty ratio are shown in the slides. The triangle gate were inspired by insects. It has much similarity with the movement of creatures, which depends the movement much on the inertia. Thus, the triangle gate is a relatively fast pattern of gates in which robots have much velocity to move forward. However, due to the robot design, the robot is not flexible as an insect. Thus, in many cases, the robot won't be much stable. Compared with the triangle gate, polygon gate considered more about how a robot gate can suitable for a machine without creature's flexibility. There are sometimes designed for the robot to adjust the robot body to a balanced position, which makes it more stable. However, the duty ratio decreases and the period of a cycle increases. So, compared with triangle gate, polygon gate has a relatively stable movement property. It is still a fixed pattern of movement. However, in real situation, a fixed pattern of movement can adjust to all the conditions, especially when the outside condition is really tough. Thus, a gate supervised by artificial intelligence was designed, which can control the robot by the information from camera on the robot body and the force sensors on robot legs. However, the sensors and the computation of AI cause great power loss, and also since every step has to be calculated accurately, it also takes a long time to do the calculation. Then I will talk about the optimization problem. The cost function is to evaluate the best pattern of gates. In my project, I choose 3 typical gates as a choice. Triangle gate with duty ratio of 1/3 to represent the most time-efficient gate. The polygon gate with duty ratio of 1/8 to represent the balance of efficiency and stability, and free gate with the average duty ratio of 1/15 to represent the most stable gate. As to the outside condition, 6 circumstances are considered, which is a combination of 2 weather conditions, non-skid and slippery, and 3 terrain, flat 15-degree slope and 30-degree slope. And according to the previous research of these gates, I formed a table of possibility of losing control, showing the left side of the slide. And our goal is to stay relatively safe in a long time, so I write down the formula. The score for losing control is the sum of the all-time multiple the probability by the sum of time. The range would be in 0 to 1, and similarly, I generate a score for time to keep the scores in the same scalar. The average velocity is shown in the table on the right side, which is also summarized from the research on robotic dynamics. The detailed reason for the distribution of velocity is presented in the print report. To form a percentage value, I calculate the maximum time and the minimum time, which is calculated in the highest velocity and the lowest velocity, means all time in gate 3 or all time in gate 1. the sum of the two scores with the coefficient as a final evaluation score. By choosing different coefficients, the user can choose a preference for efficiency and stability or balance. The variable of the problem is Tij, the total time the robot spends in gate I in case J, the number of which is 3 by 6, totally 18 variables, and the cost function is the final score. Since score P is a nonlinear equation, thus the problem is a nonlinear problem. Next is about the constraints. The first constraint is the distance from case 1 to case 6. Sum of time multiple velocity must be equal to the target distance in the corresponding cases. There would be totally 6 equation constraints. The second constraint is battery endurance should be better than the battery power loss. The rate of power loss in gate I case J is shown in the table. So the sum of power loss should be less than 100%, which is an equation constraint. The third constraint is time should be non-negative, which is a low boundary for the variables. Next, I will talk about the results of simulations. I code the algorithm in MATLAB using fmincon to solve the nonlinear problem. 4 target paths are designed to test the algorithm. The 4 paths are a combination of the relatively long and short total distance and relatively more and less slippery road. Target path 1 is in short distance with short slippery road. Target path 2 is in long total distance with short slippery road. Target 3 is in short total distance with long slippery distance. And target 4 is in long total distance with long slippery distance. The total length influences the total working time. Long total distance will make the battery constraint works too. The slippery distance will show how the algorithm works. Then comes to the experiment. Since the score are also need the user to input a preference coefficient A, I set the coefficient from 0.1 to 0.9 with interval 0.2. In another word, I set totally 5 experiments with different coefficients, the result of which will be represented in the next 3 slides. This slide will show A equals to 0.5. The slide shows the result of A equals to 0.7 and 0.3. This slide shows the result of A equals to 0.1 and 0.9. By observing the table with A equals to 0.1, it is easy to find that all the time the robot is in gate 1 in any row, which means the algorithm becomes meaningless. By observing other results, the result with A equals to 0.7 has the relatively balanced plan judged by the experience of previous research. Thus, the algorithm may have a preference on the time efficiency itself, since the balanced value A equals to 0.7 rather than the middle value A equals to 0.5. Thus, I add another extra experiment to show extreme preferences on stability with A equals to 0.95. This is the result with A equals to 0.95. I also compared the preference coefficient with each other for the robot on the same road, which is shown in the next 2 slides, which are the table formed by extracting from each row of the original table. These are the results on target path 1 and target path 2 with different preference coefficient. These are on target path 3 and target path 4. From the experience of previous research, I generate a form of recommendation preference coefficient table shown in the top of the slides. By analyzing all the results, I summarize 3 conclusions. The first one is, while users choose different preference coefficient, the algorithm can generate a related plan which satisfies the user's preference, which is my aim for the algorithm. The second is the algorithm generates a similar plan when fixing a set of preference coefficients. However, as there are still constraints to consider about the battery loss, the strategy to generate the gates plan has to satisfy the constraints. The third is the final evaluation score has no more meaningful property than a cost function to be minimized. In other words, comparing one evaluation to another is meaningless because the preference coefficient and the target path are different. The final part is to show what to do. As the time and computation resources are limited, only three typical gates with fixed duty ratio are chosen to be the choice. However, there are still many patterns of gates to choose. Besides, the duty ratio is a continuous domain, which means the choice of gate can be infinite, by doing which the robot can certainly know what is the best pattern, which realizes a part of artificial intelligence. Thanks for your time.